All right. Hello, everyone. Welcome the day after a test. Here you are. Appreciate your all's resilience. So this is and I should clarify, this is the multiple choice distribution. There is no way we're going to get your all's free response are going to take like a couple weeks to grade. That's just the reality. It's 290 free response things. So the goal is that within a week or two of the test, which was last Tuesday, those will all be graded. But that's only 20% anyway, so it's not like a huge amount of it. So multiple choice. There you go, just to clarify that. So here it is in all its glory. This is with there was a 3% curve. I detailed in the announcement I sent out, I put the details where that came from. There was a single question that less than 50% of people got right. About 30% of people got right. And what's really interesting is it's a conceptual question that you generally, pretty much everyone probably answered in about 15 seconds. So that's kind of interesting. I will go over what question that is this coming Tuesday. I have like a few makeups, just like literally a few more. So I can't go over specific problems until then. I sent out an announcement about that. So Monday's the last day of makeups, and Tuesday I have normal office hours. But I'll go over that question on Tuesday, and then you can almost guarantee that a question like it will show up on the final. The reason I add the curve for that is if everyone's missing that question, that means it's me, basically. So as weird as it sounds, the test is also a testing me, and how I did in preparing you all, more as on a whole. So to that end, how I decide curves is based on how I decide whether or not to add any points is based on that. Is there a specific question or questions that the vast majority of people miss, in which case the only common denominator is me? So I had points because of that. But it was just one question. Every other question, basically 50% or above of people got correct, so that's a good sign. And that worked out pretty well. So yeah, here's the distribution. I am very happy with this. So the average was more of like the average was give you all the exact average on here. There's some weird stuff here. The exact average was a 70.6. So with the 3%, that comes out to a 73.6, which I am very happy with. You all will see in your future STEM classes that 60s are more generally the averages on tests, if not lower. If you haven't seen that yet, it'll start to happen in your engineering courses where it's a thing. And that gets into test design and all sorts of interesting education ideas. But for me, I'm very happy with this. To give you all a sense, so you can see kind of how you compare to everyone. The reality is, in life, it's not necessarily how you do in life, it's how you do compared to other people. It's going to sound really rough and competitive. But think about when you're applying for a job. Who gets it? It's a comparison. When you're thinking about when they're doing layoffs, who are they going to decide to lay off? It's a comparison. It's a really rough idea, and it's not very fun. It's not very pleasant to think about. Work together, all that kind of jazz, but it's a reality. So this gives you a good metric, kind of how you did this comparison. To that end, my metric, to give you all a sense of what I kind of deem is really good. So if you do the math, 50% of the grade in this class is purely, I'm going to kind of call it effort-based. You got clicker questions, recitation activities, the quizzes, all of those, if you kind of put in the effort, you get all those points. Like those are generally, you put in the effort, you get that kind of 50%. The other 50% is tests. So if you do the math, if you get the 50% from effort, what do you need to get an A in the class? You need to be averaging an 80 or above on tests to get an A in the class, assuming you get all the other points. That's just how the math works out. So, and that there's logic behind this. In my opinion, if you're scoring above an 80% above my test, that shows mastery of the subject. That to me deems it in. So it works out the way I want it to. A 60% or above is what you need to get a B in the class. If you're averaging 60% or above on tests, you will get a B, assuming you get all the other 50% of the points. So, and that also aligns, if you are getting above a 60, that shows understanding. You may be like, but something 60% on this test does not mean you understood 60% of the content. As weird as that sounds, you understand more than 60%. You can't get a 60% without understanding a good amount. That is just the reality. As weird as that sounds, they don't actually correlate in that way. So to that end, that is why 60% or above for me is like a B in this class. I'm happy if people are getting above a 60%. The higher above it you are, the more you understand, / the better the test is for you. There is also the variables of like test taking skills and all that nonsense that we can't avoid. That's also kind of chalked in there. It's when you're below a 60% that there's kind of concerns. And this does not mean you're a failure. This does not mean that you're not capable of doing physics. I do not want you to take a low score in a test and take that to mean you have no hope and everything's just terrible and you're an awful person and all that jazz. No. All it means is that going into this test, on the test, you just didn't understand the Physics 1 concepts. That does not mean that you're not capable of understanding the Physics 1 concepts. That just means that's what happened. We have time. We have time to determine why that happened. And to that end, there is the bread and butter problem. Like if you have not been doing the problem sets and the quizzes and all that, that's the easy that's the easy case. If you haven't been doing those things, that's the easy case, the wake-up call of, okay, I should be doing those things. If you're in the harder case, if you've been doing all those things, you've been solving the problems, you've been able to do them without looking at worked out solutions or having someone guide you through it. Like before the test, you can do all the things. So that's a little bit more of a nuanced conversation of what's going on, and that's where I encourage you to chat with me and I can work with you to figure out where the gaps are. But that's more nuanced and it's kind of individual to each person. So if you're doing all the prep work and you're scoring poorly, that's a more nuanced conversation. If you're not doing all the prep work and you're doing poorly, it's very straightforward. Here's how to proceed. So there you go, y'all. There they are. All hope is not lost. The final does replace the lowest test grade. So if you did poorly, it doesn't mean your grade is absolutely in the trash forever. I will say people tend to perform the average for the final tends to be a little worse than the other two tests because it's cumulative. That is just, if you've never taken a cumulative final, that's just how they go. When I'm testing you on more things, it tends to go that way. So just keep that in mind. It's not, and getting a perfect score is also very hard with anything. You never want to go into something needing a perfect score or anything like that. That's a bad place to be. But there is hope. There is opportunities. But yeah, there you go. That's my contextualization of this. I am very happy with this overall. And yeah, again, if you're uncertain what to do moving forward, talk to me. Here for y'all. My office hours will start up again this coming Tuesday. Monday, I have the makeup exams. Friday, I do have some time Friday if you want to chat. I just won't be able to talk about individual questions on the test until after makeups. So if you want to chat a little bit on Friday, I can find some time. All right. Any questions about any of these things? Yeah.
Will we get the correct solutions?
Yeah, it's a good question and one that the answer isn't what I want it to be. But so currently, if you want to look over your test, you kind of have to come to my office hours to do so. And the reason for that, this may sound like a cop-out, making a perfect test is really hard. And when I say perfect, I mean with no typos. Making a test with no typos is really, really hard. And to that end, I generally don't share the tests afterwards. Like, I don't post them, because if I do, I cannot use those questions again. I have to make every single question from scratch. And it's really hard to make it perfect. And my test has to be perfect. Because if there's significant typos, it results in stress for you all during the test, which can throw people for a loop, which can totally ruin everything. So, to that end, I am thinking about in the future, maybe AI can help me check things and all that kind of jazz. It sounds silly, but genuinely, my hope is that I can start doing that. But at this time, I'm currently in the camp of, if you want to check over your test and how you specifically did, please come by my office hours and I will gladly show you your scan code and I'll gladly show you the test. I just don't send it out to everyone because at that point, once it's on the internet, it's on the internet. You can't get it out. So yeah, it's not ideal. I wish I could, I could, but then it would risk future semester tests going poorly. So anyway, it's something I am thinking about though. I'm still brainstorming it. Maybe if you all have any suggestions on ways that I could disseminate the information without giving away without putting stuff online that would make it so everyone knows, all that kind of stuff. Based on what I said, if you have ideas, please pass them to me. Because it is something I'm trying to figure out. I would love to just be able to give you all the tests and say, hey, here's all the answers and all that jazz so you can study it and all that goodness. But the reality is it affects future semesters, tests, and all that jazz. It stinks. It's not a problem I found a perfect answer to. Let's put it that way. All right. Anything else? Okay. We are starting fresh. So let me go ahead and show you all. I'm going to go to problem set 2, because problem set 2 is what the next test is going to be on. And ta-da! There it is. That's the topics we're going to be covering. It is energy, momentum, and then universal gravity and center of mass. So the main points on this next test will be energy and momentum. And then we'll sprinkle a little bit of universal gravity and center of mass. Universal gravity is really straightforward and simple. Center of mass, I won't be that mean with it. It can get really gross. I won't be super mean with it because it's not the priority, but I do need to teach you all how to do center of mass because in your future classes, center of mass is like a really, really useful thing. How do you figure out? Yeah, we'll get to it when we get to it, and I'll sell you on it then. The good news is the math is much easier on this test. Energy is a scalar. No vectors for energy. Momentum is a vector. We're going to have to deal with that. But energy is a scalar. The math is really simple for energy. The concepts are both simple, but the more you understand it, the more complex it gets, which sounds weird. It sounds counterintuitive. Usually the more you understand something, the easier it gets. But energy is one of those, the more that you think about it, the weirder energy gets in your mind. And I'll make that point today, honestly. But the math is really straightforward for energy. Conservation of energy is like one of the easiest things, but it's incredibly powerful. It's really straightforward. So energy should be pretty much no problem. Momentum, we're going to get some vector stuff there. It's just going to get more mathy. But this test generally goes better than the first test for a few reasons. One, you've already learned all the skills, like write your givens, missing. You've learned the problem-solving process. I am only giving you all 2 new variables. So I'm going to give you the unit for energy is going to have its own units. And there's going to be power. And that's it. Like, that's the only 2 new variables. We're still going to work with distance, so x and v, and acceleration, velocity, all that jazz, forces. But it's only 2 new variables in this entire thing, which is kind of wild. So anywho, this second test should go better. It generally did. The last year, I think my average was like 5% higher or something on the second test. So yeah, we'll see. But it's a good time. It's a nice fresh start too. So getting into, let me make certain I actually hit the button. I did hit the button. All right, so getting into this energy, we're going to spend a lot of time today just on the concepts. As weird as that sounds, right? We're going to sit in the idea of energy for a while. So work and kinetic energy, we're going to talk about what it is, how it's present in the world. We're going to talk about work and how it relates to energy. Then we're going to talk about kinetic energy and power. A lot of what we're going to, when we talk about energy, you all probably learned this in like middle school. Kinetic energy, potential energy, kinetic. Even if you never took a physics class, I can almost guarantee you've heard those words before. There might be some people that haven't. That's fine. I'm going to teach it to you as if you hadn't. But the good news is it's not new words. And it's going to be the same equations you learned way back. The kinetic energy is 1/2 mv squared. Potential energy due to gravity is mgh. So you probably have already learned those things. Anyway, I want you all to spend some mind energy. Well, that sounds like it. I want y'all to spend some energy to decide what is energy. If you had to describe energy to the person next to you, or an elementary school kid, what the heck would you say? What is energy? Think about it. All right, so what are some ideas y'all have? We'll get some interaction here. Yeah. Movement of atoms, all right? So there's some energy associated with movement of atoms. What else? Mass or momentum. Okay, we're going to find some. There is a relationship between mass and energy, that you can convert mass into energy and vice versa, which is one of those weird things, but we're not going to cover it in this class, but I'll mention it. Yeah.
Energy is the friend we made along the way.
Energy is a friend. You're going to make lots of. Well, actually, you're not going to make many friends with energy here. There's literally only 3 types we're going to talk about. But there's so many types of energy. You're going to make lots of energy friends in your classes for sure. What else? All right. So energy is one of those things that you probably learned at some point. Again, elementary school, middle school. There's different types of energy: kinetic energy, potential, thermal, chemical, nuclear, electrical, light. There is so many types of energy. But what is energy? Like, we know there's a bunch of types of it, but it's easier. I know there's a bunch of types of ice cream. What's ice cream? Milk, sugar, all that jazz. What the heck is energy? And the explanation I'm about to give, so I'm going to give you all a quote from Feynman, because I think it's the best definition of energy I've seen. And it's not very it's probably not going to be very satisfying to you, but it's just to get a point across of how weird energy is. So this is Feynman, famous physicist guy. I just really like this quote here. It's the most abstract idea. It's a mathematical principle. So it's not actually something you can measure. Well, you can calculate it based on measurements, but it just says that there's some number, some numerical quantity you can calculate that does not change when stuff happens. So it's basically a math trick. I calculate the energy, something happens. So it's just a description. It's just a strange fact that when you calculate this number and then stuff happens, you get the same number at the end. That's energy. Yeah.
I've heard of this equation called E equals mc squared.
Yep, so that's the
energy.
Yeah, so E equals mc squared, that's the one. So it turns out you all also heard energy can't be created or destroyed, mass can't be created or destroyed. There's like a little asterisk next to both of those. You can actually convert mass to energy and energy to mass, which is like weird. So you can, I guess, destroy mass, and in doing so it makes energy. If you have matter and antimatter, they annihilate and turn into energy. Also, when fusion happens, you have 2 protons that come together. The mass of one proton and the mass of the other proton, when they come together, the mass of that new helium atom is actually less than the mass of the 2 that went into it, and that conversion of mass goes into energy. That's the most you're going to hear me talk about E equals mc squared. It is energy. But yeah, it's just, energy is just something that you start with some amount and you can change it to other things and you can calculate it and it just stays the same. It's really weird. So then it gets into, is energy a real thing? And, most of physics is made up. Like fields, no one can see a field. You can only see the effect of a field. Energy, no one can see energy. You can just calculate it based on other things and it happens to stay the same. So to that end, this is where I told you all, the more you understand about energy, the more uncomfortable / weird it is. It's not actually a physical thing, but we can use it to figure out stuff. So it's a tool. It's a way of approaching problems. And again, it's really weird because it's very consistent. So again, does that mean it exists? What is existence in this case? What does it mean for energy to exist? Anyway, to that end, the reason I mention this is one of the most common definitions of energy is the ability to do work. And then the most common definition of work is to gain or lose energy. And so you can see the problem there. Work is defined in terms of energy. Energy is defined in terms of work. You get a circular logic and you get nowhere. So this is the best definition I found for it. And it's kind of hard to put your finger on. Basically, it stays the same. The entire energy in the universe stays the same. You calculate it at some point, some time passes, you calculate it, it stays the same. Weird, right? But it's very useful. My goodness, is energy useful. We're going to do some problems with it that you could not do with kinematics or forces, at least not with giving yourself a migraine. All right. So yeah, it's something we made up to understand the world. That's kind of the category I put it in. It takes a bunch of different types. You cannot be created or destroyed with a little asterisk. You turn it into mass. That's kind of weird. It's a scalar, so that's exciting. It only has magnitude. We do have negative energy. The only reason negative energy matters is negative energy is smaller than positive energy. When we talk about energy, all we kind of care about is if you're gaining or losing. Positive or negative, whether or not your energy is positive or negative, doesn't matter unless you have a reference. Negative 100 is less than 100. Or less than 0, less than 100. So negative energy just means a smaller amount than 0. That's it. So we'll see that eventually. But yeah, it's weird. All right, to that end, we're going to actually start with, okay, I'm not going to have you all do this, but just to show you all, you can't solve this problem, but I just want to prove to you all why is energy so useful. So one of the things we're going to learn in this class, I gave you all inclined planes. Inclined planes are so, you might not have liked them, but at least they're straightforward. It's literally a straight line. What energy lets you do is solve problems like this, which is disgusting. Like that ball, and you could have friction. Well, let's say there's no friction here. Even if there's no friction, this problem is disgusting because gravity pulls down and you'd have to find the component of it that's parallel. And then at some later point, that component's different. And so to actually solve this, you basically have to do it numerically. Like you have to have a software do this problem for you, or use energy. Yeah, either use your like kinematics and forces and do some awful numerical computing that a computer does for you because it's too hard to do analytically, or you use energy and it's really easy, super, super easy. So that's one of the really easy examples for why energy is great. Lets you solve problems that otherwise just are a nightmare. All right, so I'm just going to immediately jump into work because there's not much preface for this. This is the science definition of work. Work is a measure of the energy transferred to some object. And honestly, the best way I recommend you all think about work is whether it's how much energy something gains or loses. That is one of the best ways to think about work. How much energy something gains or loses to the environment around it. And this equation is how we can calculate it. It's the integral of f dot dr. It's a dot product, which unless you're in Calc 3, you probably haven't seen before, but I'm going to try to teach you a little bit about dot products today. A dot product can be written as the magnitude of the two vectors times cosine of the angle between them. So A dot B equals the magnitude of A times the magnitude of B times the angle between them. So if that's A, and, spooky. Oh, I think it's because of the cable. Weird. I have no idea what's going on. I'm just going to leave presenter mode and hope that fixes everything. All right, you got A there. You got B here. And you have some angle between them. Okay. So I'm going to focus on the dot product aspect of this first before we get into actually using work. But it's an integral. The reason you integrate is as something goes over a path, the force might point this way, but dr points this way, and at different times, it points in different directions. We will see that today. Don't worry, we'll get to the integral part. We'll get to unpacking this. I do want to point out, if it's a constant, you don't have to integrate, just to kind of clarify this. So if the force is constant and the path does not change, you get FD cosine theta. That just comes from, take this integral. If F is a constant, pull it out. If the angle is a constant, pull it out. What's the integral of dr? That's literally just how far you go. So if it's a constant, it's really nice and straightforward. We're going to use that a little bit. So we're going to spend a good amount of time just on this today. Even though it's both simple and not simple, we're going to spend a decent amount of time today. But I'm going to start with understanding a dot product first, because a dot product is one of those things you're going to see a lot, and most people have no idea what they're doing when they do a dot product. They can do the math, but they don't understand where it comes from, and it's much simpler than it seems. Yeah. Yep.
Well, who came up with the work to find the equation for work?
It's a good question. So something I'm gonna have to look into to give you an exact answer, but the reality is my best guess for this is gonna be they discover that energy is conserved with gravity. So they actually started with potential energy, and then they used potential energy to discover work. Which sounds weird because I'm not teaching potential energy first. And then the equation for potential energy would have come from experiments. So yeah, the discovery of a lot of work stuff came from experiments. They found that if you calculated certain quantities, they stayed the same. That's the really weird and unsatisfying thing about energy is it's just something they found. Hey, if I calculate this here and I calculate it later, these things stay the same. And then from that kind of comes this equation. It is a very good question though. So yeah, it would have come from the potential and kinetic, and this would have come from that. But we're going to start with this first, just because it's classic. Oh yeah. What is the joke of the day? Thank you.
Give it on test day.
I did forget. Did I give it on test day, or did I skip that one too? Oh, it's devastating. You all had to go into the test without it. All right. All right. How many times can you subtract 10 from 100? Just once. After that, you'd be subtracting from 90. There you go. Isn't that good? Your life is improved by that joke. All right. Now, so again, I'm going to start with this dot product first, and then we'll actually get into using it, because if we don't understand the math, we can't use the equation. So, I have two vectors here. I have A and I have B. And they have some angle between them. This question is asking if I want to find the part of B, the component of B, that is parallel to A, how would I find that? How would I find the part of B that is parallel to A? There's a component of B that's parallel to A. There's a component of B that's perpendicular to A. How would you find it? And my reminder to you all, anytime you see the word components, right triangles are involved. How would you find the part of B that lines up with A? The key is, can you draw the right triangle? That is the key to this problem. Can you draw the right triangle? All right, I'll give you all like 10 more seconds. Take your guess if you're not sure. You get 75% of the points just for guessing. All right, 5, 4, 3, 2, and 1. All right, so here's the trick. You need to draw a right triangle. B better be the hypotenuse of your triangle, because that's if you ever find components, they should be smaller than that. So to that end, ta-da, it's a right triangle. It's a right triangle where this side of B is parallel to A, and this part of B is perpendicular to A. I found the part of B that lines up with A, and I found the part of B that's perpendicular to A. Why is this useful? Why did we spend the time on, so you know the answer here is going to be cosine. Why is it cosine? You want the adjacent side. You have the hypotenuse. Cosine of theta equals adjacent over hypotenuse. The hypotenuse is B. The adjacent side is B parallel. All right. Why was this useful? So a reminder to you all, this is what a dot product says. This is one of the rules for dot products. A dot product is equal to the magnitude of A times the magnitude of B times the cosine of the angle. So using what I just showed you all, what is a dot product doing? It's literally just multiplying A times the part of B that lines up with it. That's what a dot product does. When you do a dot product, you're just multiplying the parts of the vectors that line up with each other. At some point in the future, both in this class and your other classes, there is two ways to multiply vectors. Dot product is one. Cross product is the other. Cross product is the magnitude of A times the magnitude of B times sine of theta. So when you get to cross products, what are you doing there? You're multiplying the parts of them that are perpendicular to each other. And depending on what you're trying to calculate, this will make sense. So by understanding what a dot product is, it's going to help us understand work. When we talk about work, so work is the dot product of F and dr. It's the dot product of the force. It's so weird. What is that? It's spooky. All right. It is the dot product of F and dr. Dr is the direction you're going, and F is the force. So long story short, we care about the force that lines up with the direction you're going. If it doesn't line up with the direction you're going, we find the part of it that does. That's what work is figuring out, how the force and the direction line up together, and you multiply those values together. So to that end, we're going to do a few problems on this, a few clicker questions on this to kind of make sense of this whole thing. And we will specifically look at force being constant. So I hold a 10 kilogram weight above my head for 5 minutes. How much work did I do? And I'll remind you all the equations. Work equals F dot dr, which equals the integral of F dr cosine theta. And if the force is constant and the angle between it and the direction you're moving is so if F and theta are constant, then you get work equals FD cosine theta. So there you go. What is the work? How much work did I do on the weight? You're going to see there's some terminology we have to be careful with. How much work did I do? How much energy did I add or take away from the weight by holding it above my head for 5 minutes? All right, we'll go to like a minute 20 on this. All right, we'll close it out in 5, 4, 3, 2, 1. All right, so there's a few ways to think about this. We'll do it mathematically and conceptually. So remember, work is adding or taking away energy from the system. If it's sitting above my head, and you look away, and you look back, and it's in the same place, did anything change? No. I did not add or take away any energy to the system. It is not able to do anything, like nothing changed. Yes, it tires you out and all that kind of jazz, and that gets to be a complicated question of what's going on inside your body and all that kind of jazz. But as far as we care, like on a macro scale, the weight did not gain energy. The weight did not gain any energy or lose any energy. And also to that point, how do we prove that mathematically? It didn't move. It didn't move at all. So if D is 0, the whole thing's 0. So there you go. That's kind of an example. Now, something I'm going to kind of clarify. Positive work means you're adding energy to the system. Negative work means the system is giving energy to stuff around it. You're taking away energy from the system. So that's something that we're going to kind of see, and I'll keep reminding you all of. All right, great. Here's a problem. A box starts at a height of 3 meters and falls to the ground. How much work does gravity do? I not only have to say, so I have to give you all, I also have to say what's doing the work. I have to clarify that. So the last problem I said how much work did I do? And this problem I'm asking how much work does gravity do? You have to specify what's doing the work. What force is doing it, or is it all the forces together? I will take all the equations and put them on here again. And I highly recommend you all draw your arrows because it's going to start mattering. If not now, a little later. You need to know the angle between those. Alright, we'll go like 2:15. Alright. In 5, 4, 3, 2, 1. All right. So, how do we figure this out? Well, we first decide what is the force that we care about. It's gravity. So we're going to need the force due to gravity. So you know what? Let's use this equation. Let's use the gross one just to prove a point. So we're going to do the force due to gravity, dots the distance. We're going to go ahead and change that to force of gravity times dr times cosine of theta. And you're like, why am I doing an integral? This is just to prove a point. This is just to prove where the equation came from. You don't have to actually integrate anything here. All right. Which way does I care about the angle? I need to make the decision. Does the angle change over time? To do that, I have to know what the heck the angle is in the first place. What's the direction of gravity?
Straight down.
Straight down. What's the direction of dr, the path I'm taking? Straight down. And then you add all those up, so the angle stays the same. In fact, the angle is 0. Theta is 0. Cosine of 0 is not 0, it's 1. If you got a little nervous there. So it's the integral, and the force of gravity in this problem does not change. We're going to learn it in 4 weeks' time that gravity does change depending on your height, but only like in extreme cases. Within 3 meters, it ain't going to change much. So we can pull out the gravity. We integrate dr. dr is just the path you take. What's the integral of the path you took? It's literally just how far you fell. F times d. Oh, look, it's the equation I wrote down here. FD cosine theta. We just got rid of the theta preemptively. If you want, you can put it right there. Ta-da! Look, you all derived the equation for a constant force. All right, fantastic. That was a lot of extra work for what? Just to prove that. So m times g times d. That's it. Mass is 2 kilograms. Distance is 3 meters. G is 9.8. Now, this is a magnitude. It's the magnitude of the force. Magnitude, always the question. Do I put positive or negative 9.8? Doesn't matter. It's the absolute value. It's going to get rid of it anyway. So, you plug in the numbers and you get this answer. You plug in 2 times 3 times 9.8 and it gives you positive 58.8. Now, this angle is very, very, very important. It's so important. I'm going to ask you the same question. But there's one difference. A 2 kilogram box starts at the ground and gets lifted to 3 meters. How much work does gravity do? Is it positive 58.8, negative 58.8, or 0? It's going to be the same equation. So you have to go through the math and see what's going on here. Make certain you draw your arrows. Make certain you draw your arrows. Even though it's a scalar quantity, you got to draw the arrows to figure out this angle. All right, we'll go to 2 minutes. And 5, 4, 3, 2, 1. All right. Reminder to you all. This is the angle between F and D. It's the angle between F and that's the direction you're going. And the force vector. That is where this came from. So, it's gravity. Gravity points down. The displacement vector in this case points up. Which way is it going? That's the direction of the vector for displacement. So, the math is identical. mg times the displacement times cosine of 180. The angle between them is 180. So you get negative. And the unit here is joules. All energy is joules. Work is just gaining or losing energy. It is a scalar. It still has a negative. So in this case, work, the sign here is not necessarily different. Whether it's gain, it's adding energy or losing energy to the system. And just be like, what the heck? How is it losing energy to the system? Gravity is doing negative work on it, and then the system is like the Earth box system, and that's actually gaining energy, which is weird. So by you push, so if we talk about the person pushing it, the person pushing it is adding energy to it. Gravity is doing negative energy to it because it's adding energy to the Earth box system. This is kind of a weird one to try to understand positive and negative work. I'm going to give you all some more straightforward examples about gaining or losing. But for now, what I need you all to know is this. You got to worry about the angle. Do not forget about the angle when it comes to these problems. The angle matters, and it's the angle between those two. And it's the angle between the force that we care about and the direction of motion. I could have reworded this problem and says, how much work did the elevator do? In that case, it'd be a positive energy. because it'd be a positive work. In this case, it's not a vector, even though it's positive, negative. It's not a vector, but it's gain or lose. All right. Having so much fun. Let's do another one. Same problem, slightly different. 2 kilogram box starts at the ground and slides to the right 3 meters. How much work does gravity do? And notice every single one of these, I said do not ignore air resistance. Doesn't matter at all. We don't care about air resistance. I just said gravity. For the two above it, because gravity it was moving in the same direction that gravity. So force of gravity was down, and the direction it moving was down. So if you have two vectors that are anti-parallel, the angle between them is 180. So if they're in the last problem, they're pointed the same. They were pointed opposite directions. So that was 180. And the one before that, they were pointed the same direction. So that angle is 0. So that angle is 0. That angle is 180. Because this one is 180 degrees rotated from that one. This one is exactly lined up with it. All right, I'll give y'all 10 more seconds. 5, 4, 3, 2, 1. All right, so same equation. Work equals the magnitude of F, magnitude only because the force is constant and only because the angle is constant. That's the only reason we can use this one. Otherwise, we'd have to integrate. Don't worry, I'll give you ones where you have to integrate. All right, great. Here's my box. The displacement vector is to the right. Gravity is down. The angle between these is 90. So the answer is 0. Cosine of 90 is 0. The reason is gravity is not doing anything to this. Gravity is not adding or taking away any energy from the system. Whereas when we were lifting it and lowering it, it was affecting it. When this thing moves left and right, gravity ain't doing anything related to that. It's not affecting the energy with the Earth box system, or it's not affecting the box's stored energy, anything like that. So that's the idea here. Work all has to do with, are you adding it? Is this force adding energy or taking away energy from the system? In this case, gravity ain't doing jack. It's not doing anything. It is not adding or taking away energy from the system because it's staying at the same height. All right. So this is kind of a summary of all that. So if there's a force with a component that is parallel to the way it's going, there's work being done by that force. That's the dot product. If the parts that are parallel, they contribute to each other. If they are directly perpendicular, they're not doing anything. Like it's not adding any energy to the system or taking it away. Whatever is causing the force is doing the work. So in the last problem, I said, what is the work done by gravity? I could have rephrased that. I could have changed the problem. What's the work done by the person pushing it? Or what is the work done by friction? Or what is the work done by all the forces? We're going to see examples of those problems. So it matters what's adding energy or taking away energy from the system. Just kind of zooming in on a part of it. What is this piece doing to it? What is this piece doing to it? And let you kind of zoom in on various aspects. Positive work, you're adding energy to the system. Negative work, you are taking energy from the system. Where is it going? To everything around it. So the next problem, we'll kind of talk about that. And then you might have to draw a free body diagram to find some of these forces. We'll see an example of that today. So the skills that we've learned, don't get tossed in the trash can. They come up. That's nice. A lot of the stuff in this class connects together. We're talking about forces. We've been talking about forces. Displacement. We've been talking about displacement. It all builds and builds and builds and builds. But yeah, this is a nice little kind of summary of work conceptually. Work is one of those that's notoriously tricky to understand, though. I remember being in your shoes and taking this class, and I could do the math. I had no idea what work was. I knew it was something I had to calculate on a test. Like, So hopefully you have some sense of this whole gaining or losing energy. That's my hope. Who knows? All right. An object is falling through the air. What is doing work on the object? We got air, we got gravity, we got no work is done, we got the object doing work to itself. What is adding energy to the system, or what is taking away energy from the system? All right, we'll go to like 210. And 5, 4, 3, 2, 1. All right, so how do we decide what's doing work? Well, we got to decide what forces are acting on it, and if any of them have components that are parallel to the direction of motion. So, free body diagram. What's acting on my object? When it's falling, I've got gravity going down, and I've got force of air resistance. I generally kind of call that as friction. We could put air if we wanted to, but I'm just going to call it FF for friction. Air resistance is just a fancy form of friction. Oh, that's good. Yeah, so which way is this thing moving? So what's doing work on this system? Well, gravity is pointed in the same direction as the displacement. So there is a work due to gravity. I'll even write the word work, gravity. And that's going to be a positive number. So yep, gravity does work. But there is also a work due to air resistance. And that will be a negative number. They do not cancel out unless it's moving at a constant velocity. So to that end, gravity is adding energy to the system. You know, it's getting faster. Air resistance is taking energy from the system. It's not going as fast as it would have if that air wasn't there. Air resistance, literally think of what air resistance is. That box is literally colliding into air molecules and it's pushing those air molecules and adding energy to them. So, that's why air resistance is negative. It loses energy because it's hitting that air. It's not going as fast as it would if that air wasn't there. So, there you go. It's both of them. Boom, boom. All right. So this is a problem that kind of encapsulates all these ideas. Calculate the work done on a 1,500 kilogram elevator by a cable to lift it 40 meters at a constant speed. If you ever see the phrase constant speed, that's meaningful. Constant speed is always a very, 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 very important thing that you should always take note of whenever. You might not end up using it, but it's something that people tend to like glance over, and it tells you something very meaningful in physics. All right, assuming friction averages 100 newtons, what is the work done? Part B is what is the work done in the elevator by the gravitational force? Part C, what's the total work done? All right, so let's write down our givens. You know what? Actually, let's draw a picture first. Let's follow our rules. There's forces involved, so we should draw a free body diagram. Try it out. All right, so it's on Earth. So there's gravity. That one's nice and straightforward. It is getting lifted by a cable. What do we call the force due to a cable? Nice. That's going to be up because it's going upwards. And there's friction. It's moving up. Friction is always opposite the direction of motion. Always. All right, great. That's going to help us. We need that picture to solve this problem. So, step one, what's given? We got the mass, 1,500 kilograms. We know the distance it's going to move, 40 meters. And we know the force of friction averages 100 newtons. All right, what are we solving for? The work specifically done by tension. The work done by tension. It says the work done by the cable to lift it, that's tension. You have to pick what's doing the work. We're going to see that in this problem. You get different answers depending on what you're talking about. So we're finding the work due to tension. So we, integral of f dr cosine theta. We'll jot this down just to be thorough. And then we realize a few things. We say, does the tension force ever change? No, it's a constant. Does the angle between the direction of motion and the force change? Well, let's actually decide which way it's moving. It's moving up. Nope, it's always going up. Those two things always align. Long story short, we can pull those out. So we're going to get the magnitude of F, tension, times the distance it moves, times the angle between them, equals the work to do that. And we look at that and say, do we have enough to solve this problem? Well, the first variable, we don't know Ft. So spend 30 seconds and see how you can figure out Ft. How could I find the tension force in this problem? Am I hinting you all? I could have asked you to find the force tension on the last test. The skills that you used for the last test are what you're going to use to find the force to the tension of this problem. The sum of forces equals MA. And remember I told you all there's something very important in this problem that's highlighted because it's so important. A is 0. It's moving at a constant speed. If you ever see the phrase constant speed, it's probably going to be important. It tells you that the acceleration is 0, and that's a really important thing to know about problems. It tells you that the net force is 0. It tells you that things aren't speeding up or slowing down. It tells you that the initial velocity and the final, like so many things from that simple phrase. So, free body diagram. Ft minus Ff minus Fg equals 0. You can solve for Ft. Really straightforward. You know Ff, you can find Fg. So, remember the skills that we learned before? They don't just get trashed. They do come up again. All right, so we chuck that over here, and we just do some quick solving. All right, so yeah, step 4. Let's find the force of tension. It's just going to be Fg plus Ff. All I did was rearrange things. So that's going to be m times g plus 100, which is going to equal 1,500 times 9.8 plus 100. Friction really ain't doing that much, but it is doing something. If you forget about friction, you get the wrong answer. I guess technically it would be within the 1 to 2%, but there's not really any rounding in this problem. 1,500 times 9.8 plus 100. So that comes out to 14,800 newtons, and that's not our final answer because I didn't care. That was just a step in the process. Remember, you always got to keep track of what you're solving for. So the work is going to equal force tension times the displacement times the angle. We just found the force due to tension times the displacement times the angle between the force tension and the direction it's moving. It's going to be 0. They are parallel to each other. It's moving in the same direction as that force, so the angle is 0. And you plug all that in and you get 5.92 times 10 to the 5 joules. The answer is 592 kilojoules. They're the same number. All right. Part B is more the same, but I just say, hey, find the work done by gravity. So the tension force is adding energy to the system. It's lifting that thing up. The force and the displacement are in the same direction. Part B, I'm going to let you all do on your own because it's fairly straightforward. I say it's more the same. It's more the same is a better way of phrasing that. Part C, though, we can do very quickly. What is the total work done on the elevator car? I'm going to give you all about 30 seconds to think about it. What is the total work done? So what force will I use in that case if it's the total work? You're going to use the net force, so go from there. Go from there. So the net work is going to be the net force times the distance times the angle between it. It's 0. The net force is 0. And what's interesting about this problem is if you find the work done by the pulley or by the string and you find the work done by gravity and you find the work done by friction and you add all those together, you get 0. The tension adds energy. The friction takes away energy, the gravity takes away energy, and they all cancel out and the work done is 0. And you're probably like, what? Like, how is that useful? The grand example of this is the work done in the entire universe is 0. All the forces cancel out in the entire universe. So, depending on what you're looking at, you discover different things. Depends on what you want. In this case, finding out the total work done in the elevator is 0 is probably not that interesting. But the other pieces can be useful for various things. And so it's the part you care about. Zoom in on the parts you care about. If you look at the entire system, it's very often that it all cancels out. Yeah.
Is there a formula for normal force?
Yeah, it's a good question. So is there a normal force? In this one, there won't be a normal force because it's not against any surface.
If I were to draw a three-body diagram for the cable and the top surface.
Oh, that's a good point. Yeah, so the question was, what about where the cable attaches to the ceiling? That would be its own problem. So that's where it kind of it depends on what you define as your system. So in this case, this elevator is inside of a building, which in turn is on Earth, which in turn is in the universe. And so you kind of have to decide where you're going to look. And in this problem, we just cared about the elevator cart.
Could I have gotten there just by considering the normal force is going against the cable pulling up on the top?
For part C?
No, I just
for the other parts you wouldn't be able to. The other parts you wouldn't have enough. Yeah, you kind of have to just look at the elevator cart because that's where you have the most information. Yeah, you wouldn't be able to find the force due to tension because you wouldn't know the normal force. It's a good question. Yeah. There's nothing rubbing against the elevator. Well, okay, there is friction of some sort. Air resistance, or it could, ding against the wall. It could slide. Generally, elevators are sliding on tracks. They're not just free hanging in there. So you could, I guess, argue that there's maybe a normal forces kind of on the side, but they'd be kind of from all sides. And we're going to pretend that's not there. Yeah.
Plus the normal force if there was a person inside it.
So then that would be looking at the person, but the elevator as a whole, we wouldn't consider that because the person would be pushing down on the elevator with the same force that the elevator pushes up on the person. So they'd cancel each other out, which is a good point. Yeah, so it all cares about the system. That's a key part of these problems. What are you looking at? All right, so there we go. We did the things. All right. There you go. An object is pushed with a force of 6x squared, starting at 0 and ending at x. What is the work done? And all I'm doing is putting all the equations here, and you're going to get to decide which one's the right one to use. Well, maybe they're both right. Or they're both wrong. Yeah, someone mentioned that before and I forgot to change one of them. But hey, limit your options, right? Which one should we use? All right, I'll give you all to like 2:30. All right, 5, 4, 3, 2, 1. All right. So the question is, which equation do I use? Is it the first one or the second one? And how do you decide? You can only use the second one if the force is constant. My force here is a function of x. It literally is changing as x changes. If x is 1, it's different than if x is 2. It's different than if x is 3. It's changing as you're moving. So you can't use this one. That equation down there only works when it's a constant. It's what happens if it's a constant. You pull the stuff out. So we can't use that. What we can do is we can integrate. So f is a function of x, and dr is the direction you're moving. Dr is like a tiny piece of the direction you're moving. You have to realize r is just a direction, but in this case, what is our direction? X. Dr and dx are the same thing if you're moving in the x direction. Dr and dy are the same thing if you're moving in the y direction. And if you're moving in 2 dimensions, then you got to do a double integral, and that's a Calc 2 thing. Now, there is an angle between these. So, between 0 and x, we're going to say x is positive. Well, actually, it doesn't really matter whether, okay, it does. We're going to say x is positive. I should have clarified that. I should have clarified it's positive x. It didn't actually give you an option if it wasn't, but. So, to that end, the force is always positive. The force is always positive. I don't care what number you put in, it's going to be positive. And in this case, we're going to say that the direction we're moving, let's just call it x. That's positive. That's to the right. So that means that my angle is 0. So great. So let's just plug in things. So 6x squared dx. Let's put xf, I guess. Just so it's not x is an x. All right, great. So we're going to integrate that. So that's x cubed over 3 with a 6 in front. From 0 to xf, which, long story short, there you go. And that's So there you go. Now you all are seeing where the integral comes from. Now you all are seeing where the integral comes, why it's used. Sometimes you have to integrate. If it changes over, if the force changes over distance, or if the angle is changing. All right. This is kind of more the same, but we'll work through it. How much work does this force do? -2 over x on a particle as it moves from x equals 2 to x equals 5. There's the answer. Try it out. I'll write down the givens for you. How kind of me. Get in good practices. Draw the directions that they're going. It's good to be in good practice with these things. Draw the directions because you do have to decide that angle. And then after this, there'll just be a couple more clicker questions, and then that'll kind of be our stopping. We'll talk about conservative, non-conservative, and that'll be it. So hopefully I can get through those before the end. And that'll kind of close out work nicely for us. All right, so which way is force? Force is to the left. How do you know it's to the left? Plug in these x values and you get a -f. That's to the left. The function tells you the direction. Which way is x going? Which way are we moving? To the right. So we are going to plug in the absolute value. So you might have gotten lucky. And 2 mistakes might have canceled for you if you didn't do this. So it's the absolute value of that negative. So it gets rid of that negative, but then you get another negative. So 2 over x dx, but then you get a negative from that cosine of 180. So that equals -2 times ln of x evaluated from 2 to 5, and that's -2 ln of 5 minus ln of 2. And you plug that in a calculator and it gives you an answer. There you go. Fairly straightforward. For these, I generally have to give you some function for you to actually be able to integrate it. I have to give you the function of x, or you have to be able to figure out how the angle is changing with time. That's trickier. All right. So I'll leave this for a couple of seconds, and then I'm going to give you all 2 quick clicker questions, and then we'll kind of close off with probably people not being happy about the answers. All right, this next one is literally just saying, remember that an integral is the area under a curve. That's literally all this is saying. The integral is the area under it. That's just reminding you of that. I'm not too worried about that. All right, great. Okay, I push a box across a rough floor in a straight line at a constant velocity. Someone else takes a crazy windy path that's shown below, also on the rough surface. If friction exists, who had to do more work? Me, someone else, or they're the same? So we'll just go to a minute on this. There's no math involved here, it's just thinking about it. All right, we'll go to 115. Give you a little bit more time. In 5, 4, 3, 2, 1. All right. The key here, the force, it is a constant. The force is a constant. You know, you're pushing at a constant speed. Each person, so we can pull that out. The force is a constant. The angle of friction is always opposite the direction you're going. So when I'm pushing this way, friction is the other way. When this person is pushing this way, friction is the other way. Friction is always opposite the direction of motion. Always. That's like one of the definitions of friction. So to that end, both of these equations are going to end up being F times D and cosine of 0. But this D is the path. It matters how far you go. You're integrating over the path. dr is the path you take. So if I integrate over dr, that's that distance. That's that distance. The path in this case matters because they're always opposite each other. Friction is always fighting you. You got to put more energy in to push something farther. You got to put more energy in to push something farther. So, someone else. All right. Great. One car goes flying off a cliff and hits the ground. A different car takes a nice, safe travel down the road and into the ground. In which case was the work done by gravity greater? You have to think about the arrows and the directions. And the question, does the direction of force depend upon the direction you're traveling? And the last problem it did. And the last problem, the direction of force depended upon which way you're moving. And this one, does the direction of force depend on which way you're moving? That's the key to this problem. Does the force of gravity depend upon the path you take? All right, we'll go to 115. In 5, 4, 3, 2, 1. All right. The force of gravity and the direction of motion are independent of each other. They are independent of each other. So the direction of gravity is always down. So what's going to end up happening is the angle is going to change based on what path you take. And the net result of that is that the work done is the same. Yeah, it's very, we'll talk about this slide next class, conservative versus non-conservative. I'll explain that one a bit more. But yeah, it's a good time, right?